Hi everyone, today I'm going to be presenting this paper U2Fusion, a United Unsupervised Image Vision Network, published in this journal in 2020. The key highlights of this paper is it's a fully unsupervised method that is no supervised uh, training required for this vision network, and also this single model is suited for multiple tasks. Is one single model can do fusion for multi-model scenes that, let's say, thermal and RGB and multi-exposure. Some images are less exposed or more exposed, and multi-focus. So I'll give you an example in the next slide. So these are some examples what I've mentioned in the previous slide. So these is the example for multi-model images. So this is the visible image, this is the infrared image. Here is also the RGB image and thermal image for MRI images, and this is the example of overexposed and underexposed image. And in the last columns, there are example for focused and near focused. That means a multi-focus images example. And in the second row, they show the result of fusion of each task and comparing it with uh, the state-of-the-art fusion method for respective tasks. Here it's for the a multi-model task. Here it's also for the multi-model, but specifically for MRI images. Here it's for the overexposed and underexposed image, and here it's written there a multi-focus image vision. So in this paper, what they show, even if they're using one model for multiple tasks, their model performs better than the previous existing state-of-the-art models for one particular task. So, so this is the basic overview of U2Fusion. So here, to fuse the images, they first concatenate two images together and pass it to a generator-like thing, which is called DanceNet, and generate an image, the fused image. And for the loss function, they use this structure. So first, they extract feature from both the images, which is more like perceptual loss method. The From the feature extraction, they measure the information using some method which I'll go in much more details in later slides, and get some weights for each image. For image 1 and image 2, let's say image 1 is RGB and image 2 is thermal, they'll give two weights uh, using this architecture or these methods to the loss function, and using these weights and loss function together, they will train this whole generator and get the final image. This is the architecture we have seen in previous slide of DanceNet. DanceNet is basically, you can think of like a generator where they get a concatenated images, I have said in the earlier slide. And one interesting thing here is they use two activation functions together in here, like one liquid relevant image together, and then finally get the diffused image. So there is not much interesting thing going on here. There is just using basic generators like thing. More interesting part is going on for the loss function calculation in the later slides. So for the loss function, how do they extract features? So for extracting features, they use VGG16, 5 layers of VGG16 to be precise. So from each layers, they get some feature maps. As always, initial feature maps are for shallow level features, and the later ones for deep level feature maps. So in this slide, we're talking about how they measure information from the blocks of VGG. So we have 5 blocks of VGG to collect information from each images, and they use this equation to collect images from the VGG16 blocks. Here they take the gradients of uh, each feature maps uh, given by VGG16 here, and they calculate it as is shown in this equation. Here is W1DR height, width, and depth of respective feature maps given by VGG16. They take the average of all feature maps and get some value. And after getting that GI for each image, for input one image and input two image, and they use softmax where they divide the GI with some C, which is predefined integer and it's positive, and they get W1 and W2, which is respective weight for each image uh, for later task to calculate loss function. So let's look at the loss function here now. So this is how they calculate loss function for loss for this architecture. So here they have two losses. One is for similarities between two images, and as we have discussed earlier, here they trained the same model for multiple tasks, and this EWC loss is for training the same model for multiple tasks. We'll go into much more details in this loss in later slides, but let's first look at this loss. Here, the theta means the parameters of the model, and d means the data. Yeah, and lambda is a constant, which is a which you can think of it as a hyperparameter, which we tune depending on our task in our hand. So for similarity loss, they took two losses. One is structural similarity loss, SIM, and MSC. So they took this loss for structural similarity to maintain structure, and this MSC loss, which is for the pixel level details. The first compared the final fused image and the image one, and yeah, given it some weight, and similarly for image two, compared it with the final fused image and the image two, and the weight got from the previous information measurement steps, and got the final SSIM loss. And similarly for MSC loss, they compared it with the final fused image and image one, and final image and image two, and multiplied it by the weight we got from the information measurement step, and I get the MSC loss. And for finally, for the similarity loss, they took both SSIM loss and MSC loss together. And for MSC loss, they multiplied it by alpha, which is a very small number. They said if they take the small number, they get better results. For the next loss, the EWC loss, they used something called continual learning, which is from these two papers. I'll not go into too much details of these two papers, but to cover basic part of these two papers, I'll take 2 or 3 slides. So we know, like in this task, in this paper, they are training one model for multiple tasks. So to train one model for multiple tasks, we can basically train it in two ways. One is joint training, where we can give all the data and train the model. Problem with this step is like it needs a lot of storage to store the data first, and the model needs a lot of time to optimize. And the next way is sequential training, where we can first train it for the first task, then we can train it for the second task, then we can train it for the third task. So I have given the 3 examples because we have 3 tasks in our hand in this paper. But problem with sequential training is in deep learning, as we train uh, task one, our model will get optimized for the first task. Yeah, and once our model is optimized for the first task, and then when you go for the next task, and our model will get optimized for the next task. When it is getting optimized for the next task, uh, it will tend to forget the parameters for the first task and the data of the first task. So even though the model is getting optimized for the second task, the model will be less optimized for the first task while training it in sequential training. And continual learning tries to solve this problem. This slide basically reiterates what I have said in previous slide. So model tends to forget the optimized parameter of task 1 when we are training it for task 2. So how do we solve the problem of forgetting parameters? So in continual learning, they use the fact that in deep learning models, we have models with large number of parameters, and we don't need all the parameters for one task. A better way of saying this is not all parameters are as important as uh, well, some particular parameters for one particular task. So in continual learning, they try to give uh, a weight to each parameter, and on the basis of that weight, they train the model for the next task. So we can understand it better in these equations. So for EWC laws, they use this equation, and here theta I is the current model parameter, and theta I star is the optimized model's parameter for the task, previous task. So they try to give mu1, which is a weight, uh, which is more of like uh, putting some importance on certain parameter for task 1 or the previous task. So mu(i) is defined as this. Given the optimized parameter, optimized parameters, how important is one particular parameter for the final results. And using these laws that try to uh, not change that particular parameters while training in the next tasks. So for experiment, they used multiple datasets for multiple tasks. So for multimodal image fusion, they use TNO dataset and routine datasets, and they show their model performs better than previous state of the arts in most of the matrices. Here, the red colored matrices are the best, and the blue ones are the second best. So here they're shown in most of the matrices. They are better than the previous state of the arts in both TNO and routine datasets. These are some qualitative representation of their model. They say their model produced a more detailed image of the scene as shown here. The model is much more detailed than the previous set of darts. So as you can see here, the sea trees are seen much better, or the clouds are much more detailed in their fusion technique. So in Rothstein dataset, previous dataset, TNO dataset, they show their model produce a much more detailed image compared to the other state-of-the-art models of that time. And also in Harvard datasets, which is MRI dataset, they also show that dataset performs better in multiple matrices, a matrix for fusion, as shown in this table. Also some qualitative results. And similarly, as TNO and Rothstein dataset, they also say their model produces a bit more detailed fused image compared to the previous state of the arts of that particular task. This is the result for multi-exposure dataset experiment, and they show they do relatively good compared to uh, other state-of-the-art methods of that particular task, and they're showing the more in many metrics they're doing better than previous state of the art, although they might not be the best in multiple metrics in some data, these two data sets, like CC and PSNR in EMP HDR dataset. In this dataset, they are not doing the best in EI and CC metrics. And this is the qualitative representation of multi-exposed image fusion. And they also claim their image, the fused image is more detailed than the previous set of the arts of that time. And that's the qualitative representation of multi-exposed image fusion experiment, different dataset. Again, they also claim they do better than previous set of the odds in this dataset too. This table represents the result for multi-focus experiments, and like the previous experiment, they are doing better in some metrics and not the best in some metrics, also the second best in some metrics. Then this is the qualitative representation of a multi-focus experiment. And here too they also say that the fused image is more detailed than the previous state of the arts. So that was it for me this time. Thank you very much for listening.